Okay, the next equation that we will need to derive is this equation, which is half mc squared equals to 3 over 2 kt. So the derivation of this formula is compulsory. So how do we derive it? Now remember, in the previous lesson, we learned how to derive this equation. PV equals to 1 over 3 nmc squared. Now, once we have this equation, we can actually combine it with another equation to get the equation that we want to derive. So can you still remember the equation that we derived in a much earlier lesson was PV equals to NKT. Now you notice that both these equations are in terms of PV. Alright, so PV equals 1 over 3 NMC squared and PV equals NKT. So what we can do is you can equate this PV to this PV, so you will get 1 over 3 NMC squared equals to NKT here. So once we have this, what we can do is we can modify a little bit. So I just show you how. So you can write 1 over 3 NM C squared equals to NKT. Now then, the next thing you can do is to cancel out the n, and then you get mc squared. Now you bring the 3 over, you'll get 3kt. Now we cannot leave the equation in this form because mc squared by itself has no meaning. Now if we want the expression for kinetic energy, which is half mc squared, so we have to multiply half on both sides. So you get half mc squared equals to 3 over 2 kt. So this is how we derive the equation for half mc squared equals to 3 over 2 kt. Now what does this equation tell us? Now half mc squared here represents actually the mean Ke of all the molecules. But when you say mean Ke of all the molecules, you are actually talking about the Ke of one molecule. It's just the average of all the molecules actually gives you the Ke of one molecule. Now how do I know that? Because this small m actually represents the mass of one molecule. So mass of one molecule, half mc squared, is the Ke of one molecule. But this is the mean square speed, so therefore this is the average Ke of all the molecules, but only represents for one. So in other words, if we know the temperature of the gas, let's say it's 300 Kelvin, we multiply with K and 3 over 2, we will get the average Ke of all the molecules. But if we wanted to find the total Ke, then we can just multiply by capital N. Means you take 3 over 2 kt multiplied by N, which is number of molecules that you get. Then you get the total Ke. And don't forget, since internal energy equals to Ke plus Pe, and an ideal gas has no Pe because it has no intermolecular forces, therefore your internal energy is only Ke. So the total internal energy of the gas is also 3 over 2 NKT. So the meaning of this term, this bracket c squared, is actually called mean square speed of all the molecules. And this symbol you cannot rewrite in this form, because this is called mean square speed, this is called square mean speed, and they are not the same thing. So right, so don't confuse the two. Now there's another important quantity that we are interested in, which is called root mean square speed. Now why do we find root mean square speed, and what is the significance? Now the problem with mean square speed, okay, this mean square speed, is the unit will be meter squared s minus 2, which doesn't indicate the speed. But if we were to root this, then your unit will be meter per second. So by square rooting this value, all right, okay, which is given by this formula, we get root mean square speed. And root mean square speed, the unit will be in meter per second. So this root mean square speed enables us to have an idea of how fast the molecules are traveling. So let me give you a summary of all the equations that we have done so far in this chapter. Now the first formula you learned was this general gas law that you can use only if the number of moles on this side equals the number of moles on this side. We have also learned this PV equals nRT, which can be used in any situation because number of moles is included. We can also use PV as NKT to find number of molecules, or in any question that involves number of molecules, because this N represents number of molecules. So both these equations can be used in any situation. And then we learned how to derive this equation from the tutorial question. Alright, and then we finally just learn how to derive this. So whenever the question requires you to find number of moles, this is basically the only equation you can use, because this is the only equation that has number of moles there. If the question asks you to find mean square speed, or actually more commonly they ask you to find root mean square speed, we can use either this or this, because only these two equations has the mean square speed here, which after we find the mean square speed, we just have to square root it to get the root mean square speed.